Mastin, who will speak on symmetry and rope-length criticality.
Okay, well, thank you very much for inviting me. I'm very happy to be here. And I'd like to talk a little bit about a project that I did with Jason, Joe Fu, and Jennifer Ellis at the University of Georgia. Okay, so we've heard a little bit about the rope length problem, but I thought I'd just mention that, at least for us, the motivating question is, what are the shapes of tight knots? And maybe a slightly more general question would be, what is the shape of critical points of rope length? So maybe it's not as tight as it can get. Maybe it's not the minimum rope length, but it's some critical point for rope length. And then another related question is, how do these configurations tie in with the geometry and topology of the space of knots? Okay, so we're going to look at some results in that direction, and this work is going to build off the criticality theory developed by Jason and Joe Fu and Rob Kussner and John Sullivan. Okay, so we saw a bit of this in the last talk, and this is maybe a slightly different perspective. So you can talk about the reach of a curve, right? So this is the largest epsilon, so that within an epsilon neighborhood of the curve, there's still a unique closest point on the curve. Right? So this is the same type of excluded volume we saw in the last talk. And again, this type of thing is really restricted by two things. We have a kink, which we see on the left here, which is basically a point where the curvature has reached its maximum value. And then we also have a constraint from self-distance, so the curve can't get too close to itself. And again, the rope length is defined to be the ratio of the length of the curve to its thickness. Okay, so the question we'd like to think about right now is, how can we prove that there are configurations that are rope length critical that are different from the overall rope length minimizer? So in other words, if you think of trying to shrink these ropes, are there places where you sort of get stuck in a critical point that maybe if you jiggled a little bit, it would then continue shrinking actually to the global minimum? Right? So are there distinct critical points for these configurations? And the methods we use here basically exploit symmetry to show that, yes, indeed, there can be critical points of these rope length functionals that are not the global minimizer. Right, so that's sort of what we want to show. There are distinct critical points. Okay, so what do we mean by a critical point for rope length? Well, it's defined in terms of these first variations, right? So what does it mean for a point to be critical in terms of rope length? Well, it means that if you have some variational field such that the first variation of length decreases, then it must also decrease thickness. Right? So I can't get any shorter without violating this thickness constraint. So that's what we mean by criticality. And then for technical reasons, which I'm certainly not going to get into now, I know there's other talks that talk in more detail about rope length, we actually use this slightly stronger condition, but as we'll see in a second, for our case, it's actually not stronger. But you should think of this as a sort of uniformity condition. If you sort of think of your variational field as uniformly decreasing length by -1, then you have some upper bound on sort of how fast thicknesses would decrease, right? So again, this is basically a technical constraint. And as we see for closed knots, we have this really pretty strong result that says if you're a local minimum, then you're indeed critical, right? So that's something that you might not expect, right? You're not running up. You're actually critical if you're a local minimum. And then again, for closed knots, if you're critical, then in fact you're strongly critical. So imposing this extra condition is actually no more of a restriction. Right? And this is in the paper by Jason and Joe and John and Rob that I talked about. Okay, so more precisely, the goal is to find strongly critical configurations of L that are different from the rope length minimum. Okay, so a little bit about the type of symmetry we're talking about here. So by symmetry here, we mean rigid rotational symmetry in R3. Right? So we're going to be using finite subgroups of SO3. And we say that L is G invariant if it's invariant as a set preserving orientation. Right? So if you have your knot, you can spin it. It brings it back to itself, and you preserve orientation. And then the symmetric version of criticality is that if you have a G invariant L, so this thing admits the symmetry, the symmetries in G, then we're going to say it's strongly G critical, right? If it's critical, just amongst the variational fields that are invariant under G also, right? So in other words, if I just look at ways of perturbing the knot that respect the symmetry that it admits, then if it's critical in that sense, we say it's strongly G critical. Okay, so our main results, if you have a G invariant link, then in fact, being strongly G critical implies that it's strongly critical, right? So it's maybe worth staring at this for a second and realizing that this really is saying something maybe surprising, right? So again, saying that you're strongly G critical means that you're critical among variational fields that admit the symmetry of G, right? So this is a restricted set of variational fields. And what this proposition says is that if you're critical among these variations, then you're critical among any variations. Right? So it doesn't matter if you relax this condition that your variational field admits symmetries of G, then you're still critical. Okay, so a quick rundown of the proof. Basically, the point is that it was proven that the first variation of thickness is superlinear, right? So so it's superlinear. So we're taking finite subgroups of SO3, which means that they're compact groups. So one thing you can do is average a vector field over this G, right? So if you have a variational field that does not have the symmetry of G, then you can average over G to get one that is symmetric. And then basically the point is if you assume that you're not strongly critical, meaning you have some variational field that violates the criticality condition, then you average over it. That generates one that does admit the symmetries in G. And then you use the superlinearity of variation of thickness to show that, in fact, you couldn't be strongly G critical. So it's sort of a converse proof here, or contrapositive proof. Okay, and then with that proposition in hand, you can show that, in fact, there's a strongly critical curve in every symmetry type of L. Right? So in other words, if you think of basically connected components of the space of a link type given by flowing under symmetric vector fields, right? Then in every one of those connected components, there must be a critical point for Ropelength. Okay. So now we can get to some examples, but first let's talk for a second about what these symmetry groups for knots can be, right? So if you take G of K to be a subgroup of SO3 that are the symmetries of a given knot, right? So this is the subgroup of rotations that a certain knot type enjoys. Then we know something about this group. And I put these question marks here because I've told many people about this, and we couldn't find this proposition in the literature anywhere, but I sort of refuse to believe that this hasn't been written down before. So if anyone knows where this theorem is, that'd be great. But basically what it says is that this group G of K, so the group of rotational symmetries of, in fact, any space curve, has to fall down into three categories, right? So either it's the trivial group, right? It's some lumpy thing that doesn't have any rotational symmetries. It's a finite cyclic group, or it's SO2, and K is a planar circle. And you can see this by using what I think is a pretty clever trick of noticing that if you act on a knot by an element of SO3, and then look at what happened along the curve, this acts as an arc length preserving map, right? It's an isometry of the circle, basically. So you can map down from SO3 into SO2, and then just use the classification of finite subgroups of SO2 to find out that these are the three choices. Okay, so here's one of our results, that for in any class of torus knot, for any torus knot, that you must have at least two geometrically distinct Ropelength critical configurations. Right. So here we see two configurations of the trefoil. Right. Here's the threefold symmetric. One has a threefold rotational symmetry, just rotating in the plane of the screen. Here's a configuration of the trefoil. Maybe it's a little harder to see that it's the trefoil, but it is. And this has a twofold rotational symmetry, just rotating in the plane of the screen. And basically, these come from looking at the trefoil as either the 3-2 torus knot or the 2-3 torus knot. So those are sort of standard pictures of them. Then if you tighten them, so these pictures were generated using RidgeRunner, then you see these two configurations. And they obviously look different. And if you notice, this thing still has the threefold symmetry. This thing still has the twofold symmetry. I guess this one looks like it may have spun a bit, so I think now it's spinning this way. And if you look at the rope lengths, they certainly seem to be different. Right? So these are two different, geometrically different critical points for rope length. Right, so what's special about the torus knots is that we know a lot about what their symmetries can be. And that's the key to trying to do this sort of thing for other classes of knots. So let me just quickly go through this. So you know from polynomial invariant arguments that the only rotational symmetries can be the divisors of P and Q for a PQ torus knot. You can certainly find one with a P-fold symmetry and a Q-fold symmetry, right? You again just take these sort of standard pictures, looking at it as the PQ torus knot and then the QP torus knot. So that tells us that there must be a critical, or I guess our result tells us that there must be a critical point that has a P-fold symmetry and a Q-fold symmetry. But what you worry about is maybe that these are the same configuration. Right? Is there a single configuration that has both of these symmetries? Right, so we must show that that does not happen. And then we rely on our result about what the symmetry group of these space curves can be. And so here it has to be finite cyclic. P and Q are relatively prime. So if it had a symmetry of order P and Q, then it would have a sort of symmetry of order P times Q, but it doesn't by the top bullet here. Right, so you could certainly try to run these types of arguments with other classes of knots, but you would need to be able to do something like this, where you can distinguish the configurations by their symmetry. Okay, so let's look at just some more examples. Here's the 2-5 torus knot, again in the same types of positions we saw before, and if we let RidgeRunner crunch on those for a while, we get down to these two. So we have a 5-fold symmetric configuration and a 2-fold symmetric configuration. Again, we see the rope lengths, and they're much different here, and that's sort of a general trend. As you go up, as your torus knots get more and more crossings, you see these two rope lengths sort of pull apart from each other. But one interesting thing that happens here is if you let it continue tightening from this position on the left, then it breaks the symmetry. Right? So here we think there's probably at least 3 different critical points. You have these 2 symmetric ones, and then this tightest one that sort of buckles and breaks the symmetry. Right, so this is the tightest configuration. It has no symmetry. So other interesting things can happen if you go up even farther and look at the 2-9 torus knot. You see these 2 configurations like we saw before again. Notice the rope lengths are even farther apart. But now we're in the group Z mod 9, right? So that thing now has a new subgroup. It's got a subgroup Z mod 3. And you can find configurations that realize those too. So there's sort of an extra one here because of the subgroups of Z mod 9. And we get this sort of neat looking configuration with order 3 symmetry. But again, if you let it keep tightening, this thing sort of buckles and the tightest configuration loses its symmetry. Okay, so one other result that's basically immediate is if you take a knot and then you reflect it over a plane, right, you get another knot, its mirror image, and then you can take a symmetric connected sum. Right? So just sort of drop the connected sum so that you preserve the symmetry across this plane. Well, then you've shown that this knot connected sum, its mirror, has a configuration with reflectional symmetry. Therefore, our theorem says there must be a critical point with reflection symmetry. Right, so I don't have pictures of that, but
You stated your main theorem only for orientation preserving symmetry.
yeah, I did. You can do it all for N03.
Yeah, so I just wondered why.
Yeah, sorry. Yeah, no, that was. Yeah, you can. Everything runs with O3 instead of SO3.
I mean, even SO3 can act
On the
for orientation reversingly on a knot. So
that's true. That's true. But I think that if you take a knot and its mirror image, and then you do reflection symmetry, you actually invert. Yeah. I have to stare at a picture. Okay, so obviously one thing you'd like to do is do this for other classes of knots and links. And in fact, we have other examples. I've just shown pictures here. You can play these games where you take some configuration, like here we have the 3 chain on the left, and then a hugging unknot, right? And that thing also has a reflection symmetry. But this clearly isn't the minimal configuration, because you do much better as far as rope length if you pulled this hugging unknot off and let him tighten up to a circle by himself, and then you let the 3-chain tighten. You should have less rope length if you do that. And then here's a picture of the square knot, also with a hugging unknot. Right, so you'd like to maybe come up with other classes of examples. And then, obviously one thing you'd love to do is prove that there are critical points for the unknot that are not globally minimizing. But unfortunately, these methods are sort of hopeless. One thing to point out is that there is good numerical evidence that these things exist. But we're basically out of luck trying to prove it with these, because the circle has the maximum symmetry. So you sort of can't distinguish distinct unknot critical points by symmetry, because the unknot has maximal symmetry. So you can't play these symmetry group games. And that's it. Thank you very much.
Questions for our speaker?
Yes. So this looks very similar to the principle of symmetric criticality, like Palais. But they're usually the G equivariant things are often saddle points.
Yes.
So these things, you had this thing, minimum implies strongly critical.
Right.
But are these other strongly critical things actually saddle points?
Probably most of them are. I mean, I would imagine that you can sort of at least see that numerically with configurations like this one on the top left, where if you actually let it finish tightening, it sort of falls off the saddle going down and falls into these non-symmetric configurations. Yeah, so they're probably not all stable. I don't know if the top right one. Do we know if that one's stable? At least numerically?
Numerically, no.
It's not. Okay,
Yeah.
so it buckles too.
Just one very quick question. You said every G equivariance class has a critical point in it. You had a minima, a theorem. Was it that, or was it that every connected component of every G equivariance?
Sorry, you're right. Every connected component.
Because they're not necessarily connected, right?
Yeah, right. Sure. You could have disconnected ones with the same. Yeah.
So you asked about the classification of the groups that act. I think there's a paper by Mike Friedman and Feng Luo that at least sketches some type of classification like that. So it's, I think they may do it in S3 rather than R3, but I think with certain obvious restrictions, fixing a point.
Yeah, we'll look there. The proof is in the paper, but again, I feel like this has to be referenced. There should be a reference for this.
All right, well, let's thank our speaker again.